This paper examines the framework conditions for safe work and physical human-robot interaction to reduce the workload of caregivers in the nursing domain. For this particular case, the transmission of forces play a major role. Because of that, currently existing standards to transmit forces to the human body are discussed. First, we analyzed the most important nursing activities to be supported by a robot manipulator. Then we conducted 2 experiments to find out whether a patient simulator behaves similar in comparison to a human while being mobilized by a caregiver during a nursing activity, and whether conventional, collaborative, lightweight robots are up to the task of handling a patient without external help, despite having a rather low payload capacity. The experimental results show that moving a patient simulator is more physically demanding compared to moving a human with similar weight, and that conventional collaborative lightweight robots are able to push and move a patient simulator weighing 80 kilograms. In this paper, which is called Towards Physical Human-Robot Interaction Using Force Support for Nursing Care Bed Activities, we examine how a robotic assistance system could be used to support during physically demanding care activities at the patient's bed. For this particular task, we identify suitable nursing tasks, compare the physical load while handling a human patient versus a patient simulator, and check whether a conventional lightweight robotic manipulator is up to the task of moving an 80 kilogram weighing patient simulator without any external help. Nursing shortage is a very urgent problem in many countries, but especially in Germany. According to forecasts, there will be a shortage of more than 450,000 caregivers in Germany by the year of 2050. Calling a second nurse for help is therefore no longer possible. Furthermore, caregivers often withdraw early from work due to musculoskeletal disorders, thus increasing the number of missing nursing staff. There are physical support tools such as patient lifters or slide boards, but these tools are only of limited help due to various reasons and very specific to certain tasks. Consequently, we think that a robotic assistance system could be of a more general help to support during a wider range of nursing activities at the bed, especially the physically demanding tasks. For that, we identified 3 key aspects which have to be dealt with in order to develop a robust system for everyday usage. These aspects are, first, force transmission concepts to a potentially vulnerable patient serving a multitude of manipulations on body anatomies. Second, detection of suitable spots to interact with the patient. And third, operation of the robot in orchestration with the caregiver for an optimal interaction during task execution. In this work, we mainly want to discuss boundary conditions that can lead us to the solution of the 3 aforementioned key aspects. For this, we use our setup, which consists of a bedside-mounted KUKA LBR EVA 7 robot, a force measuring plate that is placed in front of the nursing bed, a patient simulator with a weight of approximately 80 kilograms, and 1 or more Azure Kinect RGBD cameras for the robot's visual perception. The intentional contact between robot and human with additional controlled force transmission is a rather unusual topic, which is why the number of publications for this particular subject is quite sparse, even in the field of physical human-robot interaction. In this context, some scientific papers deal with the task of washing a patient. For example, in one work, the robot follows the human's arm contour while maintaining a force under a certain threshold. Another field of research that could be interesting are massaging robots. Here, the contact between robot and human with simultaneous application of a predefined force is intended, whereby the contact forces with the soft tissue of the human are particularly difficult to assess. It is difficult to grasp the contact properties in advance to a contact, and they also most likely vary from person to person based on the body composition, muscle contraction, and many other factors, once again showing the complexity of soft tissue contact scenarios. The last relevant field where physical human-robot interaction plays a major role is medicine. In surgeries, for example, the application of forces directly on humans by robotic assistance systems is not a novelty, but the forces applied are relatively small compared to the forces occurring during the execution of nursing tasks. Although the methods presented so far cover a broad field, to our knowledge, they have not yet been applied in the context of nursing, which adds a whole new layer of complexity due to safety reasons. For our work in the beginning, a small focus group meeting was held with 4 people attending who had a nursing background. The reason for the meeting was, on the one hand, to identify the everyday nursing activities at the bed, which require physical effort, and on the other hand, to explore cooperative activities, since in some cases the activity cannot be easily managed alone. The activities were also carried out in an exemplary fashion and recorded using the Azure Kinect 3D depth cameras for later analysis. The activities determined were then compared with the literature to obtain a complete representation, which can be seen in the table. The table shows results by Jäger et al. To determine the loads on the lumbar spine with the help of a biomechanical model. In Table 1, these values are compared with the maximum recommended lumbar load for healthy and back-friendly working. It is noticeable that the execution of most nursing care bed activities exceed the load limits and therefore has a negative impact on the musculoskeletal system. Robotic assistance systems could be used to further decrease the forces during the task executions. The creation of a realistic test scenario is an important factor for many areas of robotics. While many scientific papers deal with the generalization of robot behavior and try to represent the real world in simulations, real data remain irreplaceable for testing purposes for the time being. Especially manipulation tasks are very difficult to reproduce in simulations due to the complexity caused by the direct contact with all associated physical parameters. In the case of physical human-robot interaction, however, this turns out to be problematic, since in development the collection of data directly on humans should be avoided for reasons of safety and ethics. In addition to simulation, data collection in the nursing context in the real world would also be conceivable with patient simulators, for example. Since no other work has yet made a comparison with regard to the forces acting between patient simulators and humans, we will make this comparison with the infrastructure described before. For the purpose of this comparison, the activity of moving the patient to the bed's headboard when standing at the bedside was performed by a caregiver while standing on a force measuring platform. The activity was performed 5 times. The experiment shows that for a test environment similar to that of a real human being, patient simulators either need to be equipped with better mobility or they need a lower weight in order to map the potential load forces for a person with more weight. It must be said, however, that the experiment is limited to the performance of one specific nursing activity and the results may vary significantly for other activities. Another important aspect which is necessary for the investigation of physical human-robot interaction in the field of physical assistance in care is the payload or the potential of the robot to move larger masses. It is well known that robots are capable of moving large masses. However, the potential maximum payload depends on the design of the robots, the configuration of the robot in respect to the patient, and the maximum torques at the relevant joints. In nursing, however, it is also necessary to have enough space for the collaborating nurse, which is particularly important here, since most collaboration robots are built smaller and have lower payloads than common industrial robots. In our example setup, the manipulator with a maximum payload of 7 kilograms is used. However, for healthcare support, the robot has to cope with the patient's weight to provide physical relief. For this case, we have carried out a joint load test experiment where the robot manipulator should independently move the patient's simulator by pushing it within the bed. For the experiment, the antefactor presses on the upper arm of the patient's simulator, which can be seen in the image on the lower left, and thus moves it sideways by an amount of about 10 centimeters without additional help. The resulting external torques at the joints were observed over the time, and the experiment was repeated 8 times. In all experiments, it was possible to move the 80 kilogram patient simulator by about 10 centimeters without external help. This reveals 2 important points. First, the robot's payload is not decisive for the maximum applicable force to move masses, and second, it is necessary to optimize both the configuration to support without disturbing the caregiver and the joint payloads of the robot for maximum exploitation of the push potential due to the robot's maximum allowed joint torques. In this paper, we were able to collect important aspects for the approach to the topic of physical human-robot interaction in the care domain. There is a general need for physical relief and care. For this relief through robotic assistance, however, a force application directly or indirectly on humans is necessary. Safety standards with values for force limits depending on the body part do already exist, but these were not created with the intention of providing relief and care and are currently only means to an end. It requires a systematic creation of care-related force limits. When testing care-relevant robotic support movements, initial experiments using humans is not desirable, and one should switch to patient simulators for this particular task. In the present paper, however, it could be shown that there is a mismatch between patient simulators and humans, which must either be taken into account, or developments in this field must take place so that simulators become more similar to humans with a suitable weight, material and mobility. Finally, we were able to show that even collaborative lightweight robots can apply enough force to independently move an 80 kg patient simulator in bed and are thus also suitable for nursing activities. In future work, we will focus on directly supporting caregivers using robots and on measuring and comparing the degree of potential physical relief. For this, the three main difficulties on this complex project mentioned at the beginning have to be considered more intensively in follow-up work. On the one hand, an additional assessment of physical properties may possibly provide an advantage in the transmission of force. On the other hand, nursing activities at the bed are such highly complex activities that this problem should perhaps be handled by a controller learned through reinforcement learning rather than using a handcrafted controller. Overall, there are still many areas where the present system can be further improved and used for research. We envision a system which ensures significant physical relief through human-robot interaction and cooperation, while maintaining safety standards with regard to maximum force limits dependent on the patient's condition.